Okay, the addition of two spin 1/2 particles. This is a quantum mechanics problem that pops up in pretty much any quantum mechanics textbook or any course you're taking, I'm sure, if you're just learning Introduction to Quantum Mechanics. So it's good to get familiar with it and go through it. It's not a hard problem, but when you're first learning quantum mechanics, at least I found that a lot of the time it just felt like random math and I didn't really know what I was doing with matrices and stuff. So sometimes it's good just to go through it and walk through it with somebody. So hopefully this video helps with that. So the problem is we're trying to find the spin squared operator of a combined system of two spin 1/2 particles. So that can be written, first of all, as the spin squared operator is equal to the addition of both of the spins squared, which can be expanded as the spin squared of each added together, plus this cross term, the dot product of S1 and S2 times 2. And of course, S1 and S2 are just the spin 1/2 of each particle. So recall that, say for S1 or S2, I'll write it for S1 but it applies to both, the spin squared operator's eigenvalue is going to be 3/4 h bar squared, which more generally for a spin particle of spin s is s plus 1 h bar squared. And the eigenvalues are going to be the spin up and the spin down case, which corresponds to any Cartesian coordinate you choose. So I won't get too much into that, but most often that's written as in the z direction. That would be 1, 0, 0, 1. Okay, what else can we say about this? Not much. This applies to both. What we could do is write out really quick the actual spin matrix for one particle, because we're going to be writing down the matrix for two particles together. So if that's confusing, it might be easier just to start with this. So for instance, for 1, we can write the matrix as 1, 0, 0, 1 with a 3/4 h bar squared out front. And so now if you take either of these eigenvectors and you apply this matrix to it, so for instance you take spin 1 and you do the matrix multiplication, you're going to get the eigenvalue equation that this will be 3/4 h bar squared times the same state. So you can see it's a proper eigenvector and eigenvalue because applying the matrix is just ends up being this number multiplied by the original vector. Okay, so I don't want to bore you, but what does this matrix actually mean? What's with the 0 and stuff? Do these like cross terms mean anything? They do. In this case, they're kind of boring because you just have the two states and no mixing. They're two eigenvectors. So what we've got to realize is what this matrix can actually be written as is 1, 0, 0, 1. If you're familiar with bracket notation, this is like you have the bra 1, 0 over here, and then 0, 1. So the two possible states are 1, 0, 0, 1. You're just writing them as a transpose over here. And over here you've got 1, 0 as kets and 0, 1. Okay, and if you're not familiar with bracket notation, you can just think about 1, 0 is the same as the vector 1, 0, and 0, 1 is just the vector 0, 1. And if you wrote it the other way, which is called a bra, and these ones up here are called kets, this would be just the transpose of this one up here. So that would be 1, 0. Okay, so it's just listing all the possible ways which you can apply a bra and a ket together, or you can apply one transpose vector to the other one. So that's all this really is here. And you'll see what we do in the case of the total spin squared. It's going to leave us with non-zero terms on some of our diagonals. So we'll see what comes of that. Okay, so just to start off, we're going to rewrite this expansion up here as s1 squared plus s2 squared plus 2. Remember, the dot product is just all the components multiplied by each other. So this would be like the x components of each multiplied by each other, and the y components of each multiplied by each other, and the z components multiplied by each other. Still not too useful because, of course, you can't know the spin in either combination of two directions at the same time. So what do we really do with this? Well, there's this trick, which I'm just going to steal from a textbook like everybody else does, or online information, that you can write. Well, first of all, if you haven't learned this, it's not a big deal, but if you have, recall that the lowering and raising operators can be written as just combinations of spin in the x direction and spin in the y direction as a complex number, and they're just complex conjugates of each other, so the other one's minus sy. And this allows us now to write, we can write that this dot product here, so 2s1 dot s2, can actually be written as 2. So we keep the z component just like what was over here, to sz1, sz2. But now we actually have s plus for one times s down for the other, plus s down for one, s up for the other. And the raising and lowering operators just act on a state to, so say you had the state, it's already in the up direction, so you've got a spin up particle. If you apply the spin up operator to it, it'll vanish because it can't go up any further, so that's just going to be 0. It nullifies the state. And if you apply the down operator to it, it will actually put it down. And it also slaps on an h bar to the front. And then similarly, if you've got a down state, if you apply the raising operator to it, it will be h bar times spin up state. And if you do a down state, it's already down, so it will nullify the state and you have 0 again. We're going to use this property when we write out the matrix for this combined state of spin. So if we just think about the possible ways that we can combine two spin 1/2 particles that can either be up and down, is to have them both up. You could have the first one up and the second one down. You could have the first one down and the second one up, or you could have both of them down. So there's the 4 ways in the uncoupled basis that you can write out these 4 combinations. We see that there's going to be a problem here in this degeneracy here. So we've got these 2 combinations. They're not actually going to be eigenvectors, which we'll see when we write out our full matrix, which we're going to do now. So before we get started just filling out this spin matrix, it's important to recall that if you've got 2 of these vectors, or a bra and a ket, say the bra has 2 spins for the 2 particles, let's say A and B, and then the ket has, let's say C and D are the spins, and you have a number in the middle, say it's A, so it's just a number. You can pull that number in front, and then this bracket will be 0 unless A equals C and B equals D, or in other words, AB here has to be exactly the same as CD, or else this will be 0. So this is going to be important when we're combining different spin states. So you'll have to remember, if you've got just a number in front of the 1 after you put in the eigenvalue, and then you apply the bra to it, it's going to be 0 unless they're exactly the same. Okay, so let's get started. Let's just look at this first entry to begin. So what we're going to do is just be applying this spin squared operator to whatever state that is in the column header here. And then after we do that, we'll slap on whatever's in the row, and that'll leave us with this final number that we're going to put in. So for instance, for the first one, let's start. So we've got spin squared on up, up. So S1 squared, that'll be just the regular 3/4 h bar squared. So 3/4 h bar squared. Plus you've got spin squared 2, so that's also up. And it actually doesn't matter if it's up or down for spin squared. It's always, for a spin 1/2 particle, going to be 3/4 h bar squared. Okay, so what about the z direction? So that does depend on the direction. In this case, they're both up, so it's going to be h bar over 2 for each of them. So you multiply 2 times h bar over 2 squared is going to be h bar over 2. Okay, now if we look at these last 2, they don't actually matter if we're just considering this first term, because if we apply either one of these operators to it, well, there's a couple things wrong with this. First of all, no matter which one we choose, one of them is going to have one of the spins is going to have the raising operator, and they're both up, so it's going to nullify the state either way. But even if it didn't, and it just changed, say, both of these arrows to down, or it changed one of them to down, it'll never be able to produce a non-zero value when we apply this bra after, so we don't have to worry about it. So in this case, we can just add up these terms. So we've got 6/4 plus 2/4. Did I do that? Sorry. Yes, that's right. So 6/4 plus 1/2, it's just going to give you 2 h bar squared. So that's going to be our first entry here. So I pulled the h bar squared out of the matrix here, and I continued filling out the diagonals, which is easy to do. You just keep doing that above procedures, so just applying s squared to each of these column headers, and then applying the row header to each one, and getting a final number. So let's start with the off diagonal terms now. So let's start on the first row here, and on this entry, we're going to have the up down, and all we've got to do is see if there's a possible way that we're going to somehow use this spin squared operator to turn this up down state into an up up state, so that it's not 0 when we apply this afterwards. It's got to end up being whatever's here on the left. That's the rule. So if we just look at this, well, we've got to look at these two combinations of raising and lowering operators at the top right here. And we can see there's actually no way we're going to be able to get a spin up state as is here on the left, because we've got one up, one down, and these operators only ever flip both of them at the same time. So we can either flip this one to down up, you know, or nullify the state, but we're not going to be able to do anything else. So these entries are just going to be 0. The same logic is going to apply to this one right beside it, of course. The down up, it's the exact same thing. And then down down, same thing. We can only ever change both at the same time. So there's no way we could flip that to a spin up state. So these are all 0. So that was easy. Okay, and it's the exact same argument for this bottom row. So I'm going to go put some zeros here. And then, of course, it's symmetrically the same thing if we're trying to change down, down, for instance, over here on the right side to up, down, or down, up. So these are zeros. And then going back to the first column, it's going to be the same thing. It's going to be 0, 0 over here. So we're just left with these last two terms. And we've just got to figure out, well, we see we've got a down, up here at the top and an up, down here. And symmetrically, we have an up, down on the top on the second column and a down, up on the third row. So if we look at these operators, the raising and lowering combinations, there is a way, if we're flipping both, we can change down up to up down, certainly, if we change both at the same time. That would be this one right here on the left. So this would be raising the first one, like up here. This would change this to up, and it would lower the second one. So we would actually get the state we're looking for. So this is, well, we could say good news. Let's see what we get. S plus 1, S minus 2, applied to down up, is going to give you, we're doing h bar. Remember, the eigenvalue you get each time when you flip one is h bar, so it's going to be h bar squared when you flip both. And that'll be the opposite state, flipping both spins. Okay, so we're just interested in this eigenvalue here, which we got because after we slap on the other state, which is in the row, so that'll be the same thing. And we're going to be left with the bracket notation of just an expectation value, and this is just a number, so we just end up getting h bar squared. So we'll throw in the 1 here, and it's going to be the same argument for over here. Just due to symmetry, they're exactly the same. Okay, so we actually have our matrix now, and we just got to decipher what this means. So right away we can see from this, from the first column and the last column, that we've got two of our eigenvalues, which is, for both of them, it's going to be 2 h bar squared, and that is for the states up, up, and down, down. So just kind of what we were thinking, we're going to have these as eigenvectors, but these weird mixed ones, the other two, are not necessarily going to be the eigenvectors. Okay, first of all, let's just one more thing. Remember that the general eigenvalue for spin particle of the spin s, so I don't know what I'm writing here, not s plus h bar, s plus 1, h bar squared, is going to be the eigenvalue. So if this is 2 h bar squared, that means s equals 1. So we could also write this as these eigenvalues, these eigenvalues, we can also call them s equals 1, which they're more commonly referred to. Just like you don't call a spin 1/2 particle spin squared 3/4 h bar squared very often, you usually hear 1/2. We're going to do the same thing. Okay, so now we've got to deal with this chunk in the middle, the 1, 1, 1, 1. This is called a block diagonal matrix, and we're trying to diagonalize it, just like these other two terms were diagonal in the matrix, and they had all other zeros. We want to make this so it somehow these two cross terms are 0. And the way you do that, of course, is just with pure linear algebra. So this is going to turn into a pure math problem for a second. And it's going to be really easy to find the eigenvalues and eigenvectors of this new block matrix. So we've got this general eigenvalue eigenvector equation here. So our eigenvector is v1, v2, where v1 and v2 represent the components along the up-down state and the down-up state, which were, just from our matrix, they were the two states of the block diagonal. Okay, and lambda is going to be our eigenvalue here. So you can equivalently write this as this equation. It's the same thing, just by moving the right-hand side over to the left-hand side. And then the way you solve an equation like this in linear algebra is to set the determinant of this matrix equal to 0 to have a non-trivial solution, which just means that the solution isn't everything is 0. So we can write this as the determinant of this matrix is equal to 0. And for determinant, the way you solve that is just by, first you would multiply these two together, and then you would subtract the multiplying these two together. So in this case, it would be 1 minus lambda squared minus 1 is equal to 0. Okay, so this is an easy equation to solve. 1 minus lambda squared is equal to 1. So of course, 1 minus lambda then, if it's a real number, is going to have to equal plus minus 1. Okay, so then that means lambda has to equal 2 or 0. It's 1 plus 1 or 1 minus 1. So now we have our eigenvalues and we just need to solve for our eigenvectors. So to get the first eigenvalue, lambda equals 2, the corresponding eigenvector, we just plug lambda equals 2 into the eigenvalue-eigenvector equation, and we get this matrix equation. And these rows are both going to give you the same equation. So for instance, if you take the first row and multiply it by this vector, you're going to have negative v1 plus v2 is equal to 0. And then this bottom row, if you multiply that by it, you're going to have another equation, v1 minus v2 equals 0. And since they're equal to 0, these are exactly the same equations. You just multiply both sides by negative 1, and you'll see that. So what we have is v1 has to equal v2 then. And if we're normalizing the state, v1 equals v2, we have to have the state, remember, the square of the state is going to have to equal 1. So that means if v1 equals v2, and these are the components along these two spin up, spin down, and spin down, spin up, we're left with the eigenvector. It has to be 1 over root 2, the state up, down, plus the state down, up. And remember, this is just so that the inner product of the state with itself is going to have to equal 1. Okay, so now we can plug in the other eigenvalue. So if we have lambda equals 0, you're going to have 1, 1, 1, 1. So an even more boring equation, and of course this equals 0. And with the same logic, with just the difference that now you have v1 equals negative v2, you're going to have your state being 1 over root 2. And hopefully this is starting to look kind of familiar if you've seen this before, minus down, up. So this is your state. Okay, so we have solved for the eigenvalues and the eigenvectors of our 4 different states now, so we can write it all together. So you're left with these 3 states that have a spin squared equals 1, and these are the eigenvectors for them. And you also have this one state with the spin squared equals 0, and here's the eigenvector. So these first 3 are referred to as the triplet states, commonly, and this last one is referred to as the singlet state. So it's quite interesting. You started with these combinations of up, 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 down, up, down, down, and you end up not just getting simply those are the eigenvectors, but you get that 2 of them are, and the other 2 are these combinations of them, which were just linear combinations of the ones you started with. And this was just based on the fact that you didn't necessarily have the right basis to begin with when you're adding the states together, since there is a degeneracy. So this is just an example of this problem, and I hope it was helpful. Thanks.